I think that's very new. If you want to go to mathematical biology model, it should be a new one. And a second order differential equation, and PDE, and the theory. So usually the nonlinearity in logical models, so we can deal with such kind of function. So first one. So this is everybody I think are familiar with. And there's if you consider there's a phi and a long here, there are two functions, but maybe not a continuous. So usually the model is continuous function, but we allow this is a function not a continuous. And I usually think about the function in LP. So in this case, the function. So difficulty is the function taking negative value. So for positive case, that's why I'm interested in the new model there. So right-hand side is a positive, and we have a classic theory we can use. But if taking negative, that's difficult, very challenging. So therefore, more general one is G and H. So the function, so we consider omega is 0, 1 or 0, t or whatever in one dimension. And omega is in Rm, so m greater than equals 2. So that means we'll go to PDE in that case. So GH and satisfy Carathéodory function. So in X, that's measurable. And in U, second one, U is a continuous function. So if the function independent of X, so this function must be continuous. And also they can control by LP function. So here is some kind of model here is usually people consider. So we can replace left side as several operators. So first one is a fractional, and this one is very new right now. So PM here is polynomials, okay, polynomials, and n equals 1. So this is similar to first order ordinary differential equation. And the second order is in general. So A, B, C is some kind of function. So, and maybe continuous, maybe not continuous. So we need to decide that. And Stir-Liouville and differential operator, so PCO. So recently, we solved this linear case. So give a condition, PCO, and satisfy certain condition. So this is a linear case, have a unique solution. So in the textbook, and you can check the differential equation textbook, they just suppose PCO such that the linear case has a unique solution. They never tell you what's the P and the CO. So therefore, right now we solve this problem, and we give the condition for PCO. So there's a uniqueness you can satisfy. So, and general case is a PDE, so the content is a lot of things. So usually, right now people work on the Laplace case. So, but there's a first derivative here, and there's a convention case. So, and they do not study a lot for general case. Now for the system, so there's several types of system, including predictor pre-model. So I just write down some of this. So we need to know the function B1, B2, or psi phi stands for what kind of condition. So the system has a solution, at least one positive solution, and a non-zero, okay, non-zero. So zero solution in this already, sometimes zero already solution. So therefore, we want to know if there's a non-zero positive solution. That means U satisfy always a positive, but not equals 0 some point. and or everywhere positive in omega. Omega is an open set. So therefore we study. So we such kind of model here. So this one is more general, and some author already did this kind of model, but in L is capital L here as a Laplace equation. So they're looking for lambda 1, lambda 2, and they only got a sum of lambda 1, lambda 2. That's not optimal. So that's not a very good result. But they already published in JDE and several papers there. So a lot of people studied that. So right now we have a fixed point index theory. So I myself and my collaborator set up this one. So this is, I think this should be a very powerful method to dealing with existence of a solution, non-zero partial solution for such kind of a model. So there's of course there's a difficulty. So here, and a very challenge. So there's you have to overcome and some kind of difficulty here. Otherwise, you cannot do it. So you cannot use this theorem to fixed point theorem to solve the problem. So now there's this thing. So even right now, this theorem we cannot use to solve the model. You can see here. So usually you can add some term here, first one, the first part. So it's Ali effect. I think Professor Chen yesterday mentioned that's the first order. So they have such kind of things. So right now I don't know how to do that for this case. If you have Ali effect here, so there's no idea. But maybe very challenging, uses a theorem, fixed point theorem. So you can go into do that, but how to do it, we don't know. So, okay, so our main purpose will go to study existence and the uniqueness or non-existence of non-zero, non-negative. So this is a non-zero, non-negative means this, and strictly positive. So we can justify the solution and strictly greater than zero everywhere. So sometimes then F, so I already gave you F before, the right-hand side, the terms is continuous, but this is be careful, and some fractional differential equation and the PDE, they're low solution, okay? The function F is phi precise, continuous, sorry. So they're low solution. So this is a, how did it go back? Oh. Oh, the finish, no, not yet, not that fast. How they can go back? This is back. Okay, so here. So the function here, you can see the function and phi and mu and continuous, even continuous, there's no solution in the theory, we can prove that. So therefore, if you set up the model, you're just going to do it, they have a trouble. So you have a problem here. But I think a numerical method, they can whatever, even no solution, they can go into got a solution. So therefore, but in the theory, and we cannot do that. There's no solution, so we can justify. So therefore, we need to search for which kind of a function and what kind of a lambda they have a solution. So for example, for this one here, so we need to go to decide and precise the non and alpha. So how you can justify the self-solution. So, and what's the lambda? So there's no solution. Sometimes or phi precise, there's no solution. So if the not continuous, there's more challenge as well. So usual method, what we do, we're going to change the differential equation into the Botra or Hammerstein equation or some kind of operator equations. So usually it's PDE, and we will use this one. So because we cannot find a kernel green function, it's not difficult to find a green function in that case. So therefore for PDE, so we were going to, and there's some general operator there. Now we can use a theory here. So first one is a fixed point theorem. That's used to find a non-zero solution, non-negative, okay, degree theory, of course, but it's not non-zero, or not non-negative. And fixed point theory, usually Ballah contraction, something like that, and a variational inequality. So this one, and last one is very new as well. So how you can use variational inequality theory to get a non-zero, non-negative, positive solution. Okay, the challenge thing is if you want to get a good optimal lambda and a function and the nonlinearity, so there's some kind of thing you have to go to solve. So you will need to set up some kind of theory, new theory. That's why right now the people cannot get a good lambda, the eigenvalue, the lambda 1, lambda 2, because there's some theory we need they cannot follow. So therefore, there's a first one is compactness. So nonlinear map, and you have to go to show this is compactness. If you want to use a fixed point index theory, the big difference is problems green function in the kernel and have singularity. So an dominant convergence theory, you cannot use it. So that is cause trouble. So, and in the fractional differential equation, a lot of people made a mistake. We have thousands of papers, wrong paper, because they treated the singularity as a continuous function. So therefore, they made so many wrong paper right now for the fractional differential equation. And also how to show the map is a nonlinear and lower norm out map. So for the fixed point theory, if you want to use. And another one, everybody familiar with limited in-frame or supreme function. So you know the definition usually in R1. But if you go to product Ballah space, there's a challenge. Okay, there's a challenge how you can use that. So you usually made a mistake. Okay, use the idea from one dimension, you made a mistake. So how to compute the supreme and limited supreme or limited in-frame in product space. So for example, you have a population model in the system predator pre-model. So right-hand side, the term, how you can go to compute limited in-frame or supreme. So such kind of theory, we need to go to setup. So otherwise, you cannot work on it. Okay, so this is, I don't think I can finish everything. So this is a first order, I want to mention this. And there's a more there's a new one actually. So although so many people work on this, so and this is similar to first order differential equation. If you take n equals 1, and this is boundary condition. So here, and you not require has a derivative everywhere on AB. So usually first order, you started the model, and you have to suppose the function u is defined everywhere, right? At least it's belongs to absolute continuous function. So therefore, this is a challenge part. What's the meaning of mathematical biology in this case? Because this is really weak. U is not has a derivative everywhere. So this is some kind of information about Botra integral operator. And that's the challenges you can see here's x equals y, that's a singularity, that's unbounded. You cannot use regular Lebesgue dominant convergence theory. So therefore here for compactness And the continuities operator, that's always cause trouble. So the people ignore this, they treat this as a continuous function. That's why they cause a lot of wrong paper here. So there are several type fractional differential operator here. So and a very interesting one is a capital. You can see here, they suppose if n equals 1, so they have a first derivative. The first derivative, but not everywhere defined. And this together with the integral, then this equals right-hand side. So right-hand side can be your logistic model. And so therefore it's contain a first order differential equation. So therefore, some of you, if you study the first order or system, so maybe you can consider set up your theory to the fractional and differential equation here. So this is a difference nth order and mean value theorem. So recently I solved this mean value theorem. Everybody understand what's a mean value theorem. And you can see you are going to require and function continues and has a derivative everywhere. So, but right now this we do not need that. So derivative maybe exist everywhere. So mean value theorem is everybody's, if you know the calculus, right? So you want the f prime has a derivative everywhere inside, okay, inside AB. But right now it's not necessary. So we will have that. So that's first things. And the second thing is we have non-constant equilibrium. You never made. So non-constant equilibrium. So if you start a first order system of a first order differential equation, only constant equilibrium there. So there's a difference. So you be careful. So if you go to start a system of first order fractional differential equation, so that's the case. So we have an example here to show you, and there's a non-constant equilibrium here. So this is a mean value theorem. Okay, so that's a classic one. So f exists everywhere on AB, inside of AB. So we got this. So everybody familiar with this one. So it exists one number between AB. So for the fractional one, so there some change, but they do not require f has a derivative and everywhere in AB. They just suppose f is an absolute continuous function. So absolute continuous function has a derivative and everywhere, almost everywhere. So therefore they cannot have everywhere in this case. So therefore this is a more general case. So okay, there's an example show you, and a classic mean value theorem cannot apply here because the derivative does not exist here. See, this function derivative does not exist. So therefore, mean value theorem for classic one cannot be used here. And so for fractional one, we can use it here. So therefore, this is something new here. Okay, so this is a method, I think no more time. And the challenge here is singularity. I already mentioned that. There's thousands paper. So if you want to search the wrong paper, you should go to the fractional fractional case, fractional calculus. This is ton of paper wrong. So very recently, I got a two paper. That's a correct version. So if you want to do the first order and system, I wish you go to study this paper and make sure you're everything correct. The second one, so GDE this one. So this is a higher order. This is the first order. So this is a nonlinear and large vein equations. This is from physics, and almost all the result I saw is wrong. So many people work on this equation here, but none of them I saw this correct. Okay, so And therefore, we have to going to redo this. They always suppose f is continuous, but unfortunately, this transfer this one to integral equation, that's not equivalent. Okay, that's not equivalent. So differential equation go to integral equation, two equations are not equivalence. So therefore, what they're doing, they're looking for the solution for the integral equation, not original equation. So therefore, all this part right now, we need to redo right now. So therefore, I wish you have students interested in this part, I'll go to work on it. And for example, here is I give you two recent paper. So this kind of a paper is all wrong paper. So this is here. So potential topics in fractional calculus, so theory and application. So even first order, and we need to going to set up the basic theory. So basic theory, existence, uniqueness, local solution. So everybody familiar with this one for ordinary. So first order differential equation. But right now for the fractional, what we're going to do. And also the nonlinearity f, right-hand side, is not continuous. How to do that? So usually first order, the theory, you can say the function suppose f is continuous. So that's why I'm looking for the result, even for the first order. So right-hand side is not continuous. What's the theory here? So for the existence. So of course, nonlinear not given equation, we need to redo it. And a biological interpretation, because there's a fractional reasoning from physics. Okay, originally from physics. So right now, how about a biological interpretation? First derivative, what's its meaning from there? And modeling, and how to do that. Use a fractional to model. So not only rate of change. So first order, the derivative, I'll explain that. So therefore, I think it's quite interesting. So I wish some researcher and graduate students, and wish them go there to work on it. And also Canadian mathematician, so many work on the mathematical biology. So I think if all together, we can get a good things from here, this part. So because original model from physics, how they can use this one to the mathematical biology. So that's interesting things. So what time I finish? How much time? 7 minutes. Okay, now we go to second order and Stir-Liouville equation. So this kind of equation for the first order, and basically, and f is not continuous, we set up a result with my student here. And we can show first one and the second one. And first one can derive to Stir-Liouville equation. So this is a boundary condition contain and several boundary condition here, Newman boundary condition and a Robin boundary condition here. So for this one, so they contain several. So this we work on this case. So usually the boundary condition, the parameter here is always positive, and so many people work on that as positive. But very recently, and we with Professor Wu and Xiao Yi, our previous postdoc, and we solved the problems and parameter, the boundary condition parameter take a negative value. And we derive the green function and also some kind of vector function we can transfer to this case. So which contain negative value. So we give an example there. So after this, so how you can find a solution and a non-zero solution, and if f negative, so the mathematical biology model, how we can get an existence for the solution. So there's quite a new, nobody do it right now. And also I do not have time to work on that. Maybe in the future, my students can work on that, ask them to do that. So the parameter take a negative, and how to do this kind of existence. And so I said first order and Stir Liouville differential equation with my students. And so there's a part how to use the fixed point theory for nowhere outcome map to solve such an equation. So we did something, and because of the challenge, how to show the operator is nowhere outcome map. So that's a difficulty. And also how you can show your solution is strictly positive solution. That's a very, very challenging. The two things very challenging. So if you overcome that two, so you can go to the paper. So right now my students, one is Zai Yi in the Waterloo, I think that with the engineering, two supervisor, and Chang Wing, and go to Queen's University, I think with the Professor Days, so there. So potential topics system, so, and even one, first in one dimension, so system we have not to do it. So when we go to one equation, so for the system, that means you can use to predict model. So this is how to do this kind of predictor model. So this in the future topics. So how to do the first order in one dimension. So how to do that. And for the system, so always difficult here. And also, D part negative here, how to do this case, D negative. So if you move this one to right-hand side, so you can treat this as D is negative, go to right-hand side, this is positive, right? So minus D is positive. So this term we can explain this as stalking. So in the application, that's how to deal with the stalking. So what's green function and how to go to so existence of a solution. So this is a topic we are working on it right now with my future graduate students. So second and PDE. So this is more general right now. So in the 2 dimension at least, greater than 2, and the boundary condition here. And so this is a more challenge for this case. So right now, and this is a special case. So Laplace equation diffusion motivation, and this case for the first case. So boundary condition contain, and at least we know there's 3 cases, and Derek and Newman usually people work on the Newman boundary condition a lot of paper. They do that because it's a little bit easier. So recent paper, so we did this one only for directly boundary condition. I did this one with Professor Lin Wei in Fudan University. So this paper already published. And the second one is system. So this paper not published. So the challenge is how you can show the green function or the operator, and it's nowhere out one all dimension. So how to show this is a nonlinear map. It's a nowhere normal outward map if you want to use a fixed point index theory. So this theory, how you can go to lambda, very good lambda. So right now, the people only work on the Laplace equation, and so Laplace equation and the lambda just take some of them. Some of them depends on the x. That's not very good. So therefore, we want to go to improve such kind of a result and got an optimum interval or interval for eigenvalues. Okay, thank you.